Hello Math 3311 students. Welcome to Number Theory. Here's Lesson 0, Preliminaries. This is an optional lesson, so if you feel comfortable with all these preliminary materials, then just skip altogether. That's fine. If you decide to stick around and do some review, that's good, but you may want to do some fast forwarding here and there. You can do that at any time, at any place. Okay, let's begin. Section 1, Set and Relations. What is a set? What do you mean by an element? Roster notation, set builder notation. You should remember all those kind of things. What do you mean by a subset and superset? When the two sets are the same. So subset one direction, subset another direction. When you have to prove two sets are the same, then typically you'll have to prove these two. And then we use this script P notation to denote a power set, the set of all subsets. So a certain set S belongs to the power set of A means S is a subset of A. By the way, we have two different notations for a subset. This notation and that notation, they're the same actually. Historically, they are defined the same. If you want to have a proper subset, strict relation, then we have to use these notations. A is a proper subset of a B is a proper superset of A, those kind of things. So, and the relationship between less than or equal versus greater than doesn't work like this for sets. Set algebra and Venn diagram. Okay, here we go. There goes the complement. Intersection. Union. Difference. Set difference. And then symmetric difference. In terms of logic, this is not A and B, A or B, A but not B, and finally A XOR B, A or B but not both. And then here are some set operation rules. We call those Boolean algebra, named after British mathematician Boole, I think. I forgot his first name. Anyway, it's called Boolean algebra, and we have all these rules. And finally, sets of numbers. Please remember, whenever you see double stroke fonts, they are sets of numbers. At least in algebra, they are. In topology or geometry, things may be a little bit different there. And then we use these superscripts to denote positive integers, negative integers, or non-zero integers, and so on. For complex numbers, there's no such thing as positive or negative, so we have just non-zero complex numbers like that. So remember what these superscripts mean. Alright, so much for subsection 1, set. Now, how about functions? Let's begin with the Cartesian product. The set of all ordered pairs is called the Cartesian product. And by the way, what is this x comma y? What's the definition of this ordered pair? As a matter of fact, we define like this. And consequently, this one here is a shorthand of this. You see, we have power set of x union y. That's the starting set. It's one thing to have something here, but it's too cumbersome to skip, versus something here is unclear. Consequently, we may have trouble later. Turns out we don't have any trouble, so we can go from here. Next, relation. Any non-empty subset of a Cartesian product is called a relation. And an ordered pair, x comma y, belong to a relation. We say x is related to y. Some examples. Oh, never mind. One of the examples is function. And okay, alright, a relation has a domain and range. So domain is the set of all x coordinates that are related to something in y, and the range is set of all y coordinates that is related from something in x. And a function is a relation that satisfies this particular property. X and y1 are related, and x and y2 are related, and y1 and y2 are the same. So each element in the domain is related to one and only one element in the range. That's a function. And then you should remember one-to-one and onto functions. Injection, surjection, bijection. And then composite functions is a graphical expression. And then inverse function. Remember those? And finally, image and preimage. I don't know whether we are going to be using this in number theory. Probably not. So we'll skip this. For other classes, image and preimage will be important, but for this course, probably not. Next, equivalence relations. We begin with Cartesian product, and a relation is any non-empty subset of a Cartesian product. An equivalence relation is a special relation with these three properties: reflexivity, symmetry, and transitivity. Each x is related to itself. If x is related to y, then y is related to x. And finally, x is related to y and y is related to z, then x is related to z. If you have all three, then the relation is called an equivalence relation. If you have an equivalence relation, you can define equivalence class. Set of all x that is related to A. Here, A is called a representative, and then the same equivalence class may have different representatives. In that case, those two representatives are actually related to each other, and those equivalence classes must be identical. If those representatives are not related, then they're disjoint. So this is an interesting property. Two equivalent classes are either identical or disjoint. Nothing in between. No overlap, non-trivial overlap or anything like that. Completely same or completely disjoint. And then if you take the union of all those equivalent classes, you're going to have a partition because we have disjoint union. All those xi's, these equivalent classes, do not overlap each other, and in that case we use this special union notation. Do you see this little plus notation here? Let me expand the font. Yeah, that means it's a disjoint union. And some people use just dot here, but Mathematica supports this plus notation, which is a little bit better as a matter of fact. A little bit more cumbersome to write. And as for the proofs of all those equivalence classes and things like those, well, I'll leave those to you. All these are reviews, so you should be able to do all those. Now, if you take the set of all equivalent classes, and that set is called a quotient set. It's a subset of the power set, but most of the time we skip that. So what's an example of this quotient set? Well, one example is this: modular equivalence or modular congruence. We define A and B are congruent modulo M as M divide A minus B. Do you remember this in Introduction to Proofs class? You can prove that this is an equivalence relation. Yeah, okay, that's the equivalent way to define the same thing. M divide A minus B. So A minus B is some Q times M. And it's an equivalence relation, and you can actually prove it. Reflexivity, symmetry, and transitivity. Well, they're proofs, but I'll leave the proofs to you. And then they preserve the addition and multiplication. So if you have two different representatives, A1 and A2, B1 and B2, then addition yields the same equivalence class. Same goes to the multiplication. The proof is rather tedious, but you can do it. Oh, never mind. I'm not going to do the proof. I'll leave you with all those proofs. I know for a fact that you went through all these in the Introduction to Proofs class, so I'll leave you there. Okay, all right. Oh, by the way, the notation of equivalence classes, most of the time we use this bracket notation, but in some cases, traditionally we use some other notation. In this case, the equivalence modulo M class, we use bar notation for equivalence class. Where's the definition? I didn't write down all the definition here, sorry about that. The notation of the equivalence class is bar, and that's traditional for modulo equivalence or modulo congruence. Most of the time we use bracket, but there are cases we use other notation for equivalence classes and quotient sets. Okay, finally we have order relations. It's a relation too, and then partial order is a relation with these properties: reflexive, antisymmetric, and transitive. Reflexivity, x is less than or equal to x itself, okay, alright. Antisymmetry, x is less than or equal to y, and y is less than or equal to x, then x and y have to be the same. Transitivity is pretty clear. Any set equipped with this partial order is called a partially ordered set. An example of such, the subset structure in any power set. There are more, of course. Another way to define the same thing is to use strict partial order, irreflexivity. So there's no such thing that is strictly less than itself. And asymmetry, x is strictly less than y and y is strictly less than x. That's impossible. There's no such pair. And the transitivity, of course, that stays the same. And you can define a partial order using this traditional definition and define strict partial order as x is less than or equal to y but not equal. Or you can do vice versa. You can define like this, strictly less, and less than or equal as, well, yeah, strictly less or equal. Either way they work out. If I remember correctly, our Introduction to Proof textbook uses partial order, the usual one, not the strict partial order. And the strict partial order is derived from the usual partial order. Next, linear order or total order. It's a partial order with an additional structure. X is less than or equal to y, or y is less than or equal to x. We have to have any one of those. There is sometimes it's called comparability. Any pair of numbers, any pair of elements must be comparable. If so, then partial order is called a linear order, and because of this comparability, all the elements can be arranged in a line. Also, you can use strict partial order equipped with the trichotomy. X is strictly less than y, or y is strictly less than x, or x is equal to y, and one and only one of those hold, not both. So not just or, but you can use XOR. Finally, well-ordered set. What do you mean by a well-ordered set? Any non-empty subset has a smallest element, the minimum, then we call the set is well-ordered. That's a review on order relation. And so much for set theory. I reviewed as quickly as possible and as briefly as possible. If you want a little bit deeper understanding, well, there are plenty of things I skipped in this notebook, so you can study with those.